answer three things. First and foremost, we need to understand what an elastic material is. What do we believe an elastic material is? What should be an elastic material? An elastic material is a material. An elastic material is a material or substance which regains its original shape and size after a distorting force or load is applied. That is the definition of an elastic material. Are you getting me? A material that what? Regains its original shape and size. Afterwards, after a distorting force must have been removed from it. Now, what do we mean by that? What do we mean by that? Now, what we mean is that if a force is applied to a substance, are you getting me? And probably it is stretched, a stretching force or a compressional force. Is either we call it a tensional force or a compressional force. Now, if it's applied to it, and when you now remove the force, the body is able to return back to its original position. Then that body is said to be what? Is said to be an elastic material. But if it does not return back to its original position and size, or original shape and size, then you don't call it an elastic material. That's what it means. So that means by extension, the concept of elasticity is going to be the word. Elasticity is the ability for a material or substance to regain its original shape and size. Its original shape and size after an applied force is removed. Now, so a scientist by the name of Robert Hooke performed an experiment to explain this. And what he did, or the experiment he performed, is later referred to as what we call the Hooke's law. Hooke's law is used to explain elasticity of a material. So what does Hooke's law state? Hooke's law. Now, Hooke's law states that provided the elastic limit of an elastic material is not exceeded, then the extension E is directly proportional. You can just say it's proportional. It's directly proportional to its applied, or to the applied force. Or load. That's what it just means. Now, basically, what Hooke's law is trying to enlighten us on is that provided the elastic limit of an elastic material is not reached, if you don't reach the elastic limit, then of course the force would always be proportional to the what? Extension. So because of that, mathematically, we say that what? Force, based on this theory, force is proportional to what? Extension. Extension of the material is what? Is the length or the shape of the material before this distorting force is applied, and minus the length and shape of the material after the what? Distorting force is removed. Are you following me? So from here, we can say that what? F is proportional to E, where E, and from there I can say that what? F is proportional or is equal to KE, where K is the what? Constant of proportionality, which is known as elastic constant or force constant or elastic stiffness. Those are the various names for K. And of course, our F is applied force in newtons, applied force in newtons. K is on the elastic limits or force constant or elastic constant, elastic constant or force constant. And it is denoted by what? N per meter. That is newtons per meter. And of course, our E is extension, and that is in meters. Although for practical cases, it is usually in centimeters. It's usually in centimeters. But because of the SI unit, of course, extension is what? Meters. Meters. Now, you should know something, that your extension, is actually, extension is final length minus initial length. That's what it is. So you can see that E is equals to what? L2 or L1 minus L0. So that means if you decide to slot this into the formula, then it can be written as F is equals to K open bracket what? L1 minus what? L0. So it could still be written as that. Either way, you are correct. So if I'm trying to express it as a diagram, if this is the length before extension, let's call this A, B. This is before load is applied. And then you stretch it. You probably add a stretching force to it. What would happen is that this is A, this is B. So this little stretch that you have here is your extension. Are you getting me? So if you calculate the whole length, this will be your L1. And if you calculate this length, this will be your L0. So L1 minus L0 is going to give us our what? Extension, which is this small point that we have. So having done that, we now look at what? The graphical implication of Hooke's law. The graphical explanation of Hooke's law. I'll be revving up the board now. The graphical representation of Hooke's law. Now, if you look at this graphically, this is F, this is extension, this is your F that is for your load in newtons, and this is extension in centimeters. That is the more practical thing to use, centimeters. Now, when you have these parts going on a straight line, are you getting me? At this point, we say it is linear. Now, what does it mean? When it is linear, linear means that what? As F is increasing, E is also what? Increasing. It's increasing in what? In the same proportion. So at this point, AB, let's call this 0 to A. At this point, we say that it is what? Obeying Hooke's law. Are you getting me? At OA, it is linear, and it is what? Obeying Hooke's law. Because Hooke's law is telling us that what? There's a direct relationship between force and extension. So it is obeying Hooke's law. Now, and at that point, at this OA, the extension, the elastic limit has not been what? Exceeded. Elastic limit is not exceeded, or it has not even been reached. So the elastic limit has not been reached at that point. So I want you to put that in mind, get it. Now, after that point, we'll get to P. We'll get to this point. We'll get to this point. This point that I measured as A, if you just go beyond it slightly, get to P. At that point is also P. Now, P is known as the proportionality limit. Meaning that at this point, if you decide to go beyond it, then you will be moving on to your what? To the elastic limit. At that point, if the force continues, the stretching, if the stretching force is applied continuously, it doesn't what? It's at that point it cannot return back. So at that point you now have your what? Elastic limit. You can see it's bending off a bit. Tell you that, oh, at this point it will be very difficult for me to go back to my original shape and size, but well, and it still go back, but it may be difficult. Then thereafter, so we call it the elastic limit. So at this point, after this point, Hooke's law is no longer being obeyed. Are you getting me? So after this, you have your yield point. At the yield point, it means that it has lost, that is why. It means that it has lost yield point. It means that it has lost its elastic properties. It has lost its elastic properties. So at that point, even when you remove the force, it cannot return back to original shape and size. It has yielded it. It has now become what? A plastic. At the yield point, the elastic material has now changed to what? A plastic. It is now a plastic at the yield point. And then after the yield point, you have what we call the breaking point. The breaking point. At that point, it now breaks. It cuts off. Are you getting me? So it has exceeded the elastic limit, and then it now gets cut off. So this is the breaking point. At the yield point, it has become a plastic. At the breaking point, it cuts. It cuts off. So let's define elastic limit. In the real sense, the proportionality limit is where Hooke's law actually holds. Anything after the proportionality limit is no longer Hooke's law, it's no longer obeying Hooke's law. So at this point, Hooke's law is not obeyed. Why at this point Hooke's law is obeyed? So where you have this straight line, Hooke's law is obeyed. When you have this breaking and everything, where you have this, then Hooke's law is no longer obeyed. That's what it means. So you can't see that this thing is obeying Hooke's law. So if you have to define elastic limits, we have to define elastic limit like I'm about to. So let's just position the camera. So now, at this point, our elastic limit is defined as that point, or is defined as the limits of force beyond which the stretched wire does not return to its original length when the stretching force is removed. When the stretching force is removed. So it doesn't return back again. It doesn't return back. After this point, it doesn't return back when the stretching point is removed. Whereas for your yield point, so let's define yield point. At the yield point, what happens? Is the point beyond the elastic limits? Is the point beyond the elastic limit in which the elastic material has yielded or its elasticity permanently, and has become a plastic So at this point, it is not a plastic, like I said before. At the point where an elastic material loses all of its elastic property, it becomes a plastic. All right, so moving on. Let's move on to the next terminology, Young's modulus. Young's modulus. Young's modulus. Now, Young's modulus is usually represented with the letter E, capital letter E. So it's defined as the ratio of tensile stress to tensile strain. Is the ratio of tensile stress to tensile strain. So that means I can see it as what? Young's modulus being stress over strain. Now, how do you define stress? How do you define stress? Stress is defined as the ratio of force applied to the area exposed. So basically, we are saying that stress is force over area. So because of that, remember that our force is in newtons and our area is in meters squared. So that means it's SI units. Its SI units is Newton per meter squared. So you can write it this way, or you can say this. That is what? Stress. Now for strain. So in order for you to have stress, that means you are applying a force to an area. That's what it's telling you. You are applying a force to what? To the surface of the surface of a material. Are you following me? Now, strain is different from stress. Some people take them together, but it's different. Now, in the case of strain is what happens after stress has been applied. I don't know if I get what I'm saying. Strain is what happens after stress has been what? Applied. After you stress a body, what happens is what?
Yes.
If I were to slap somebody's cheek at the moment, if I give somebody a slap, why? Now, me using my hand and hitting the person and striking the person on the face is me applying force. And the person's face is what? Area. Are you getting me? Now, the swelling that will not ensue, the swelling of the face that will ensue is the strain. It's what we now call strain. That swelling that may ensue. Some people, if the person is light-skinned, that person may actually feel like, or maybe if the person looks at his face in the mirror, it may become reddish or purplish.
Red.
Are you getting me? So that tells us that is what the effect of what? Stress. So strain is defined. Strain is defined as the measure of deformation experienced by a body. So because of that, it has no units. Because the way a particular body would handle strain is different from the way another body will handle strain. So it has no dimension. It has no dimension. It has no dimension. So mathematically, it has no dimension. So mathematically, so that strain is the ratio, is defined as the ratio of extension to length. The ratio of extension to length. So strain is extension all over length. Of course, extension is in meters, length is in meters. So this and this will cancel out each other. So that's why it has no units. Are you getting me? It has no units. So I can say it is strain is E over L. Now, Let's now take it back to our Young's modulus. Remember, recall that we said Young's modulus is force over area. Or rather, sorry, skip that please. We said that Young's modulus is stress over strain. Are you following me? We say Young's modulus is stress over strain. And now we've been able to break down what stress is. We've been able to break down what strain is. I want to believe we are done writing.
Yes.
So going back to our definition of Young's modulus, we said Young's modulus is stress over strain. And we said now that stress is what? Force over area. And we said strain is what? Extension over length. Good. So from there, excuse me, we'll be able to decipher that this is F all over A divided by E all over L. And that will be F all over A times L all over E. So this is our formula for Young's modulus. Young's modulus is E is equals to FL over AE. Very simple and direct. Very simple and direct. So of course, where all of these mean their usual thing, E is Young's modulus. So that means the unit, the SI unit of Young's modulus is going to be what? Newton per meter squared. The same, that's the unit of Young's modulus. Then our F is force, and that is in newtons. L is length of the material, and that is in meters. E is extension of the material, that is in meters. And A is what? The area in meter squared. I think it's quite straightforward. So now we'll look at the last and final thing for the day. Work done in springs or elastic material. The work done in springs or elastic material. Work done in springs or elastic material. Work done in springs or elastic material. So after this is just explanation. So probably in the next class we'll solve questions on it. So now basically we know that work done is force times distance. And you can liken that to what? To this also. Work done, if you consider a spring, are you getting me? And then force is applied to it, of course it will be extended by a particular extension. So you want to find out the work done by it. So the work done by the spring, work done by spring is equals to average force applied multiplied by the what? By the distance moved. Work done is force times distance, right? Now, in the case of an elastic material, the distance moved is the what? Extension of the material. So that is average force applied multiplied by extension. Now, your average force, for you to get your average force, that means you have an initial force and a final force. Now, but your initial force will be 0. Are you getting me? It will be 0. The initial force will be 0 because at that point it's at 0 Newton. But the moment you apply the force, you've increased it all over 2. That is the average multiplied by the extension E. So that would mean that this is F over 2 multiplied by E. So usually it is written as 1 all over 2, 1 all over 2 F, 1 all over 2 F E. So from Hooke's law, we know that we can still write work done to be 1 all over 2 KE squared if you apply Hooke's law. Recall that F is equals to KE. So if you substitute the value of F in the value of F here, that will become KE multiplied by E. That is why this is KE squared. And your work done can also be W is equals to 1 all over 2 F squared over F squared over K, depending on what you're using. So, but all of them all mean the same thing. You should know that your F, your W is work done, and of course the unit is in joules. Work done, and it's in joules. Because it's energy, right? And F is force, and of course your K is what? Force constant. And E is extension. So we know all of those. So, and then you should also know that there's always conservation of energy. The law of conservation of energy always holds. Are you getting me? Elastic potential energy can be converted to what? Kinetic energy and vice versa. Are you getting me? Potential energy can be converted to kinetic energy. Kinetic energy can be so there are some questions that you are given. Are you getting me? That has to do with conversion of energy. There are some questions you're given. That has to do with conversion of energy. But that's another topic for another day. Conversion or conservation of energy. Like when you have what? When you have the catapult. Are you getting me? The elastic potential energy of the catapult will become the what? Kinetic energy of the moving stone. So like that. So do you have questions, comments? So in the next section of this class, would be solving questions that relate to conservation of energy. Do you have questions?
No.
All right. Thank you very much.
Thank you too. Bye.